Hello everyone. Welcome to ILTA Physics Online. Today, we are going to study uniform motion, which is one type of 1D motion. We already explained what uniform motion is in the previous lesson. In this lecture, we'll express it using the 5 methods that we've learned so far. And in addition, we'll describe uniform motion quantitatively using equations, so-called kinematic formulas. Up to now, we've been learning how to describe or represent motion. To put it another way, we've learned the tools or techniques for expressing motion up to this point. But from now on, we'll start applying those methods to describe specific kinds of motion one by one. That's a shift in perspective, and from this point on, the content will become more and more interesting. Shall we do a quick review of what we learned last time? In the last lecture, we explained that motion along a straight line is called one-dimensional motion or 1D motion. But even motion along a straight line can be divided into 2 cases. There's uniform motion, where an object moves with a constant velocity, and there's accelerated motion, where the velocity changes as it moves. I've repeated this many times, but since velocity is a vector, we need to understand it as either both magnitude and direction staying the same, or one of them changing. We also learned how to represent motion visually and quantitatively using position graphs and velocity graphs. When you see the graph below, I hope many of the things we talked about with these 2 graphs will come back to mind. First, the position graph by itself tells us a lot about an object's motion. For example, in the graph below, the object starts at -10 kilometers, then moves 30 kilometers to the right over 30 minutes, stops for 10 minutes, and then moves 20 kilometers to the left over the next 10 minutes. You must really understand what this graph is showing. The important point is, the slope of the position graph shows the velocity in that time interval, and the sign of the slope shows the direction of motion. On the right side, the velocity graph represents the changes in velocity of the same motion with respect to the time axis. One useful tip to remember is that, when analyzing a motion that changes direction, it helps to break it up into separate time intervals where the direction is the same. And we also learned that the slope of the velocity graph represents acceleration, and the area under the curve with respect to the x-axis represents the total displacement. Again, since we are not yet very familiar with negative velocity, we always need to pay extra attention when analyzing motion with negative velocity. As we can see, both position graph and velocity graph are very useful tools for describing motion in a precise and quantitative way. Okay, with that knowledge, let's move on to today's topic. So, let's start with uniform motion. Here, we need to change the way we've been thinking about motion. So far, we've focused on how to represent an object's motion clearly. Now, we'll use those methods to explain uniform motion itself. Do you see how this perspective is a bit different? Okay, let's talk about uniform motion now. As shown in the picture above, let's imagine a car is moving forward at a constant speed. Uniform motion means motion with a constant velocity. We've already learned 5 ways to describe motion, and we'll use them here one by one. First, we can describe an object's motion in terms of displacement or change in position. So how would we explain uniform motion using displacement? Yes, we could say, it's motion where the object covers the same distance during every equal time interval. Alright, then let's look at the second method, using velocity to describe motion. In terms of velocity, uniform motion can be described as motion with a constant velocity. If we expand on that, since velocity is a vector, we can describe it as motion with the same magnitude and the same direction. Now the third method. Starting here, we begin to represent motion visually. That's the motion diagram method using the particle model. If we draw the motion diagram for uniform motion, it looks like the figure below. We place dots at equal intervals and draw arrows pointing in the direction of motion. This way of using a motion diagram is more visual than the first 2 methods, since it shows motion in a clearer way. In particular, it also shows direction, giving us more information about the motion. This is where we really see the meaning of the phrase, "One picture is worth 1,000 words." Now, let's look at some more graphs. Let's explain uniform motion using the position graph and velocity graph that we studied last time. First, look at the position graph at the bottom left. The position graph shows the object's position with respect to time, and we said its slope is the object's velocity. Since uniform motion means motion with constant velocity, the slope is constant, and the position graph should be a straight line as shown below. In other words, if a position graph looks like this, that motion is uniform motion. Finally, let's express uniform motion using a velocity graph. This one is a bit simpler. Uniform motion means motion with a constant velocity, so the velocity graph should be a straight horizontal line. And remember, the area under the velocity graph represents displacement. So, we've now described uniform motion using all the methods we know so far. We can see that each method has its own features, strengths, and limitations. Now let's learn how to describe this kind of motion more quantitatively using mathematical equations. Now let me introduce a new way of describing uniform motion using equations, also called the kinematic formulas. When we describe motion quantitatively, we use kinematic variables. In uniform motion, we can describe the motion quantitatively using three key kinematic variables: displacement, velocity, and time. Let's start with the time variable first. As I've emphasized multiple times before, if we set the initial time to 0, the time interval is simply represented by. Let's describe uniform motion quantitatively using velocity. As you see in the equation, the velocity is constant. That's natural since uniform motion is defined as motion with constant velocity. Let's look at an example to make this clearer. Suppose a car travels 30 kilometers in 1 hour with same speed. What is the car's velocity? The question asks for speed, but since the problem doesn't mention direction, we can treat it the same as velocity in this case. From another perspective, since the motion described has no change in direction, for this time interval, speed and velocity can be considered the same. Anyway, in this case the car's speed can be calculated as 30 kilometers per hour. This calculation is very simple, but what we are interested in here is that the speed remains constant throughout the motion. Here is a useful tip. For convenience, we usually assume the initial time and initial position are both 0 when solving problems like this. Now, let's look at the equation for position in uniform motion. Our usual concern is, after the object starts moving and finishes moving, where is its final position? To find an object's final position, you first need to know its displacement. Displacement is defined as final position minus initial position. Since uniform motion means moving with constant velocity, the distance traveled in time t is just velocity v times timed. Thinking about the definition of speed, it's not surprising at all. For example, as in the earlier problem, if the car moves at 30 kilometers per hour for 1 hour, then the displacement is 30 kilometers. In the graph at the lower right, the shaded area represents the displacement. Now, let's rearrange the equation in terms of final position. From the definition of displacement, final position equals initial position plus displacement. And since displacement in uniform motion is velocity v times time, we can write it like this. If we assume initial time is 0, then the final position equation becomes this. That was a long explanation, but if you understand uniform motion, all you really need to remember is this final equation. And that's the end of our discussion of uniform motion. You should now be able to describe uniform motion using graphs and equations, and also recognize when a graph or equation represents uniform motion. But, as we all know, the real world is not uniform. So, in the next lesson, we'll study non-uniform motion called accelerated motion. Great job, everyone, and see you at the next lecture.